In this video, we're going to talk about exponential growth and decay in calculus. So recall from pre-calculus that the growth and decay model is P of t equals P naught, that's that little subscript O, or that's how it's pronounced, e to the kt. Also recall that P naught is your initial population. Okay. Also, your k here is going to be your growth factor, and if it's positive, it's going to be a growth, and if it's negative, it's a decay. And then t is our time. Okay, so understanding all these different parts is crucial to doing these sorts of problems. So our first example is going to be a word problem, and it says in a lab, the number of E. coli bacteria grows exponentially with the growth constant of k equals 0.41, and we're going to be in time of hours. Assume that 1,000 bacteria are present at time t equals 0. And our first task is going to be to find a formula for the number of bacteria, P of t, at time t. So our goal is to try to get a formula that looks like this, that is going to work for every function with this information that we want for any given amounts of t. And our first task is fairly simple. So what we're going to do first is do our P of t. And the first thing that we need is our initial population if it's given to us. And in this case it is. We know that we have 1,000 bacteria at t equals 0. That's an initial population. So I'm going to replace P naught with 1,000. We also happen to know our K, and make sure if you know that this is growing or decaying. Sometimes it will tell you in very different ways, so just be careful of that. In this case, it's just growth and growth and growth, and then k is equal to a positive number. So that's definitely very easy to tell that this is a growing function. And then we just put t. So this is our formula for any number of hours that pass. And we'll be able to determine just how much bacteria that there will be at any time. And the next part, in part B, simply says, how large is the population after 5 hours? So we're just going to take our number and plug it in for t. The only thing that I would caution you with is make sure that this unit matches the unit that you're given. Otherwise, you're going to have to convert it. Titus saw a human being outside. Sorry for his barking. Okay, so here's our function. P of 5 is equal to 1,000 e to the 0.41 of 5. So we just use our calculator to evaluate this. And we're going to have P of 5, 7,767.9. And I know I want you to use 3 decimal places. I'm getting these numbers out of our textbook. Please always use 3 decimal places. So we're going to then take a look at this. It wants about how large, okay, this population is. Well, we can't have 0.9 of a bacteria, nor could we have 0.9 of a person. So if it asks you to estimate or round, you could say that this is 7,768 bacteria. And then part C is, when will the population reach 10,000? So in this case, I'm not given time, I'm trying to look for time, and I want my ending result to be equal to 10,000. So we are going to do this like so. We're going to set our function equal to 10,000 and solve this using our logarithm properties. Okay, so 0.41 t. So the first thing that we need to do is cancel out the coefficient of e, which is going to be to divide by 1,000. And these will cancel, and then we're going to have 10 on the left-hand side equals e to the 0.41 t. And to cancel out an e, we need a natural logarithm. So we're going to take the ln of both sides. So we're going to do ln of 10 equals ln of e to the 0.41t. And recall that an ln and an e will cancel each other out. So I'm just left with ln of 10 equals 0.41t. And then to solve for t, we're just going to simply divide both sides by 0.41. And we're going to have our answer by using our calculator. About 5.62, of course, use 3 decimal places, please. I know I'm not. Hours. And so that's how we're going to solve some basic exponential function problems. So with that being said, we're going to move on to the next part that talks about how to integrate in exponential functions with derivatives and integrals. So our theorem is going to state that if y of t is a differentiable function satisfying the differential equation y prime equals ky, then y of t is equal to our basic exponential function p naught e to the kt. So how do we actually use this? I'm going to show you an example so that it makes more sense. So here's our question. It's going to say to find all solutions of y prime equals 3y. Which solution satisfies y of 0 equals 9? So we've got 2 different parts here. We first have to find the solution and then find the specific solution that satisfies this condition. So if you look back up in the theorem, notice that we have a condition that looks like this. And specifically, k is right here. It's equal to 3. Okay, so when we describe this as a y of t function, this is how it's going to change. So when I go backwards, when I do the integration of this, okay, if I know this rule, then this is very simple. We're going to go ahead and just rewrite this so that it's y of t equals p naught e to the k, which is 3t. That's how we need to use this theorem. That's all you need to do for the first part. Okay, we're going to call that part A. In the next question, it says, which solution satisfies y of 0 equals 9? If you can see that this is an initial condition, then that is p naught. Okay, so all we need to do to get the specific solution, or the particular solution, if 9 is my initial value, is to replace p naught with 9, and everything else stays the same. And that's all there is to that. Okay, so we're ready to move on to the next example. We're going to say, pharmacologists have shown that penicillin leaves a person's bloodstream at a rate proportional to the amount present. There's three different parts to this. The first part is to express this statement as a differential equation. Okay, so here we're going to go with our third and last example. So it says, pharmacologists have shown that penicillin leaves a person's bloodstream at a rate proportional to the amount present. There are 3 parts to this question. The first part says to express this statement as a differential equation. So there's a couple of things that we want to look at. First of all, we're looking for a rate that is proportional. Way back in algebra, we learned that proportional functions have the form of y equals kx. It's just when you have like the mx plus b, it's just the mx part. It's just the m's changes to a k for whatever reason. So in this particular problem, we're not dealing with x's, we're dealing with t's. So we're looking for something to be somewhat similar to this. Okay. Now we can give this function any name that we want. So we're going to use a of t as the name of my function. Okay. Now, since this is a differential equation, this function needs to be a derivative, and it's going to be equal to that proportional part. Now, the k that we have, we need to determine if it's positive or negative. In this particular problem, the penicillin is leaving the bloodstream, which means it should be decreasing. So I need to have my k to be negative. And then what would typically go next right here, we've always used t, but keep in mind that this function is representing a derivative and it has its own special rule, the rule that we just looked at, where y prime is equal to ky. So we have the first part checked off. We have our function and its derivative. We've got our k. So the only way to get y is by doing this, a of t. So this represents the amount at any given time, which is going to yield our y value. So that's the first part of our problem. All right, so our next part, part B, says to find the decay if 50 milligrams of penicillin remains in the bloodstream 7 hours after the initial injection of 450 milligrams. And also recall that the formula that we used previously, this one right here, can be transferred into a regular function like this. So again, these are really key pieces because in this particular question, it's not asking about the rate of something, it's asking about an amount. And when you're talking about an amount, you're talking about your original function, not the derivative. So to start this process, we're going to start plugging in everything that we know. And in this case, we didn't have y of t, we have a of t. That's the one that we chose. And our original from part A looked like this. And we're going to go ahead and plug in what we know. So, I'm sorry, first of all, we need to convert it, sorry. So what we're going to do is we're going to convert it into this form here. So we're going to have a of t equals p naught e to the negative k t. So this is what we're going to plug everything into so that we have our original function ready to go. So our a of t, So find the decay if 50 milligrams of penicillin remain. So that's our ending amount. That needs to be right here for a of t. Okay, it says it remains in the bloodstream 7 hours after the initial injection of 450 milligrams. So our initial amount is 450, which is going to go where p naught is. E is just E. Negative k, that's what we're actually trying to find. We're trying to find the decay factor. Okay, and time is 7 hours. So we need to just evaluate this for k, and then we will be done with this particular question. So the first thing is we're going to divide both sides by the coefficient of e, which is 450. That's going to cancel, and I'm going to begin the next step over here just to make sure I have enough room. So 50 over 450 is 0.1 repeating, okay, and it's going to be equal to e to the negative k times 7. So to cancel out an e, we need a natural logarithm. We're going to do the natural log of both sides. And the ln and the e will cancel, so all I'm going to have is negative k times 7. And then the last thing that we need to do is divide both sides by 7 to yield our final answer. So we're going to have, and then we're going to have to negate it, but the 7s will cancel. So this is what we're going to get when we do that division, and then we just have to negate the k to make it positive. So k is going to be equal to 0.314. So that's going to be our decay factor. All right, next and final part. Under the hypothesis of part B, at what time was 200 milligrams of penicillin present? So in this case, we're going to take the function that we had before, and we're going to set it equal to 200 to determine the time at which this happened. So here's the function from before. I inserted my k value into k. Okay, and k was negative, so we need a negative with this as well. And then we're going to set this function equal to 200, and we're just going to begin solving this out for t. So getting everything copied, and then we start the process. So divide by the coefficient of e, which is going to yield a 0.444 repeating. equals e to the negative 0.314t. And now we take the natural logarithm of both sides. And the natural logarithm and the e will cancel, so we're just going to have 0.314t, and then we're going to divide by that factor to cancel. And let's see what we get for t. And I'm going to get 2.586, and this is in hours, and that's it. And that will complete this tutorial.